Assalamu alaikum dear students. I welcome you to the 18th lecture of probability and stochastic processes. In recent lectures, we have been dealing with continuous random variables, and in particular, we have analyzed uniformly distributed, exponential, Erlang, and Gaussian type random variables. We worked with their PDFs and CDFs and found probabilities of interesting events defined on those distribution functions. We have also introduced the concept of joint pair of random variables where two random variables are defined in a joint manner over a random experiment. So out of one execution of the experiment, two continuous valued observations are made, and we note these observations as a vector of length 2. So this pair of random variables take on values in part of xy plane or the whole xy plane, and the joint PDF, which is a function of two parameters, is a surface over the region over which the pair takes on values. So this surface can be defined over a part of xy plane or the whole xy plane. And the height along z-axis of this PDF, which is a surface, tells you that what is the relative likelihood of this pair of observations to take on its values. In past lecture, we looked at a couple of simple examples of jointly distributed pair of random variables. This lecture is a continuation of that lecture. So we are going to look at those examples again, but we are going to discuss a few other issues. The issues we have already discussed are that out of this two-dimensional surface, which is joint PDF, we can have two one-dimensional functions which are called marginal densities. We get those marginal densities by integrating this surface along x-axis or along y-axis. And if we integrate along y-axis, the y parameter vanishes and the resulting function is a function of x, and we can call it marginal density of x random variable. And if you do it properly, this marginal density defines the behavior of random variable x alone. Similarly, if you integrate with respect to x, then x vanishes and the function you get is a variation of y. So this function, which varies as the y varies, is marginal density of random variable y, and this can describe the behavior of random variable y alone. So from joint density, you can always get two marginal densities. But if you have two marginal densities or two densities of two random variables individually, you can get to the joint density if you multiply the two densities together. So you have one density which is a function of x, another which is function of y. You multiply them together, you get a function of x and y. But this is only allowed if x and y are independent of each other. So this is also a way to check if the two random variables defined as pair and behavior described by the joint PDF are independent or not. All you have to do is find the marginal densities and see if the product of the marginal densities is the original joint PDF. To continue with our work today, let's look at the example we discussed in last lecture, where we had two random variables x and y, and they were defined by a flat type of PDF. This PDF was defined in such a way that it was flat over a rectangular region, and this rectangular region had sides which were parallel to the coordinate axis. So the extent over which this pair of random variables x and y were defined were x from 0 to 10 and y from 0 to 13. So there was a 10 by 13 region of xy plane over which this joint PDF was flat, non-zero, with a constant height of 1 over 130. In this slide, I have drawn 3 lines on top of this flat density, and they are drawn with a particular purpose in mind. We discussed that the marginal densities can be obtained from the joint density by integrating along x or y axis. But these lines are our trajectories if we travel on top of this joint PDF along coordinate axis. For example, if you look at the red line, it is the trajectory of our travel on top of the PDF along x-axis at a constant y value of 2. So if you keep y is equal to 2 and change x from minus infinity, when you reach 0, you ride on top of the PDF, you go on top till x is 10, you fall down and then keep on going. If you look at the shape of this PDF, this is very similar to the marginal PDF of x. If you remember, for this case, the marginal density of x was a uniformly distributed function with height of 1 over 10 and extent was from 0 to 10. So if you look at the first curve, which is trajectory of our travel on top of this joint PDF, it starts at a low value of x and goes on top of PDF, but for this travel the y value is fixed at 2. So you keep y is equal to 2 and change x from 0 to say 11, then from 0 you ride on top of the joint PDF, at 10 you come down and keep on going. So the trajectory has a shape which is same as the marginal PDF of x. The marginal PDF of x has a height of 1 over 10, but this trajectory has a height of 1 over 130. Even though the height may be different, but the overall shape of this trajectory along x-axis for y is equal to 2 is almost same as the marginal density of x. The next curve on your slide is a yellow one, and this is also a trajectory when we travel along x-axis by keeping y fixed at 5. And this has the same shape as the other trajectory, which is just a scaled version of marginal density of x. Similarly, if you travel along y-axis by taking x a constant of 2 or any other value, you will get a trajectory which has a shape which is a scaled version of marginal density of y. Marginal density of y is a flat function from 0 to 13, and all the trajectories here which are obtained by traveling along y have extent 0 to 13 with a height of 1 over 130, which is a scaled down version of marginal densities. So if you have a joint PDF and you travel on top of this surface which is joint PDF, and you get a shape of trajectory which is a scaled version of the marginal density, then the joint PDF has x and y random variables which are independent of each other. You will not find this assertion in any textbook. This is from my own personal experience and a closer observation of how the independent pair of random variables gives a joint density which is multiplication of two individual densities. Let's look at the other flat joint distribution that we worked with in the last lecture. In that case, the joint PDF was defined over a square-shaped region, but the sides of the square were not parallel to the coordinate axes. Actually, the square was rotated by 45 degrees and it looked like a diamond. So, the joint PDF was a flat plateau-like surface defined over a square-shaped region rotated 45 degrees with corner at 5, 0 and 5, 10, 0, 5 and 10, 5. So over this diamond-shaped region, the joint PDF was a flat function. We worked with that and we found the marginal densities also. So the marginal densities, both x and y, for this case were triangular in shape. If you integrate this diamond-shaped flat region, then the densities of x and y both start at 0 when the parameter is 0, and they reach a height of 0.2 when the parameter is 5, then they fall down, and by the time you reach a value of 10, the density has come down to 0 again. So both marginal densities are triangular in shape. The joint density is a flat region defined over a diamond-shaped region, and we also found out that in this case the two random variables x and y were not independent of each other. Let's see if the trajectory over the joint PDF can give us a hint. This joint PDF, which is flat over this diamond-shaped region, is drawn again on the slide that you can see now. And on this slide, I have also drawn 3 curves. The first curve represents a trajectory of our travel on top of this joint PDF, which is along x-axis. So we move along x-axis and keep y fixed at 2. In this case, the trajectory goes on. For y is equal to 2, x comes from low value, and when it reaches 3, it meets that flat plateau, then it rises vertically, remains on top of the plateau, comes down, and then keeps on going. So this trajectory looks like a uniformly distributed random variable. But marginal density was not a uniform function, it was a triangular. So this trajectory gives a uniform kind of function, flat function, which is not of the same extent as the marginal density. Marginal density was from 0 to 10. This is from 3 to 7, and it is flat. If you look at another trajectory which is shown in yellow, which is also along x-axis, and it goes along x-axis by keeping y fixed at 4. And this is also a flat kind of function with extent larger than the red curve. But the shape is not same as the shape of marginal density of x. Similarly, if you look at blue curve, it is trajectory of our travel on top of this PDF along y-axis while we keep x fixed at 2. And this also gives a flat function with width approximately 4 and a height which is 1 over 100. So the shape is not the same as the marginal density of y. So that should give you a clue that for this particular case, the two random variables x and y, whose joint density is a flat function over a diamond-shaped region, are not going to be independent of each other. Let's look at another example where we construct a joint PDF and make trajectories on it and see if the random variables are independent or not. To emphasize this point, I'm going to take two marginal densities of previously discussed case where the marginal densities were obtained from integration of flat plateau which was diamond in shape. I'm going to use those two densities of x and y, and I'm going to multiply the two densities and get a joint density. Since I'm intentionally multiplying two one-dimensional densities, I know that this joint density is going to give me a pair of random variables which are going to be independent of each other. So let's take these two triangular shape marginal densities. They have values of 0 to the left of 0 and to the right of 10, and from 0 to 10 they rise and meet at 5 with a top value of 0.2. So if you take two densities, one defined for x, other defined for y, and multiply them together, you are going to get a shape which is shown on the slide that you can see. This shape is like a pyramid, but it's not a typical four-sided pyramid. The sides, four sides are not flat, they are kind of bulgy, they are kind of curvy. So this semi-pyramid, as you can see on the slide, is the joint PDF. One obvious difference compared to the previous one is that the extent over which the joint PDF is non-zero is again a square, and the sides of this square are parallel to the coordinate axis, and the extent over which this square has non-zero values of joint PDF are x from 0 to 10 and y from 0 to 10. Another obvious thing to note is that if you ride along x-axis, wherever you ride, you are going to get a trajectory which is triangular in shape. In the previous two examples where I took flat type of joint densities and I drew red, yellow and blue curves, those curves are drawn manually by hand. So in this case, it's not easy to draw a trajectory which keeps x or y value constant, because the pyramid is not easy to work with and you cannot draw straight trajectories. So what I have done is I have used MATLAB and its built-in function of not a number, NaN, capital N, small a, capital N. This is not a number, a special number in MATLAB, and if for any defined surface one point is changed to NaN, it does not get drawn. So what I have done, I have generated this two-dimensional pyramid type surface, and selectively I have made 3 lines where values of the surface are not the original values but NaN. So when I draw this special surface using the MATLAB command of surf, I get the kind of graph that you see. I urge you to study MATLAB, particularly this 3-dimensional graphics thing, and when you are working with densities of joint random variables, you get densities which are surfaces. Try to draw graphs like this. Believe me, it's great fun. Anyway, looking at the slide, as breakage in this surface, so this breakage is very visible, and you can see that the first breakage is when we are traveling along x-axis while the value of y is fixed at 2. And the shape of this trajectory is again just like the marginal density of x. The extent is same, only the height is different. And if you look the next trajectory, which is shown as a breakage at a higher peak value, this is for travel along x-axis while we keep y equal to 4. And this trajectory also has a shape which is same as the marginal density of x, only the peak value is different. And similarly, if you go along y-axis by keeping x fixed at 2, you get the third trajectory, and this trajectory has a shape which is just a scaled version of marginal density of y. Hence, if you have a joint PDF which is multiplication of two marginal PDFs, then the two random variables represented by two marginal PDFs are independent of each other. Another interesting observation about these two cases, where one was the flat plateau type region defined over diamond shaped square, a square rotated by 45 degrees, and this case where we have a kind of pyramid. The marginal densities of x and y for both cases are same, but the probabilities of different events are not going to be the same. For example, let's try to find the probability of an event where x lies between 0 and 2 and y also lies between 0 and 2. For the case where the PDF, the joint PDF, was a flat region defined over diamond shaped region, probability of this event where x is between 0 and 2 and y is between 0 and 2 is 0, because on this region the PDF is 0. PDF starts to rise at a nearby point of 2.5, 2.5. But for this case where we got the joint PDF from multiplication of two marginal densities, if you find the probability of this event where x lies between 0 and 2 and y also lies between 0 and 2, you get a non-zero value, because the PDF is non-zero in this region. And if you find the probability of this event for this case, it comes out to be 0.0064, which is certainly a non-zero probability. So far we have been dealing with simple events defined on joint density functions. For example, we were interested in finding the probability of x being between 0 and 2 and y also being between 0 and 2. Let's start discussion of a case where density is flat, but the events are defined through complex boundaries which are not for this type of simple events where x belongs to a certain region and y belongs to a certain region. For events like these, the region over which the PDF is going to be integrated is a rectangular or square type region, and the square type region is parallel to the coordinate axis. The sides are parallel to the coordinate axis. Let's look at a case where this is not the case. The PDF is flat, but the events have boundaries which are not straight lines and they are not parallel to the coordinate axis. The boundaries are quite complicated. The case is a revisit of the example we discussed in previous lectures, and it is called Buffon's needle. This was originally investigated by people who were interested in finding the probabilities of events which involved geometric aspects of the things. So what they did, they drew parallel lines on floor or a square shaped grid and threw circular discs and small needles on those floors. And then they were interested in finding the probability of those objects touching or not touching a line. In previous lectures we have discussed this, and the example where the floor was marked with square grid and a circular disc was thrown on that has been thoroughly investigated. Let's continue and see if we have a floor marked with parallel lines where line spacing is h, and then we throw a small needle very thin with length L on that floor, and then we try to find the probability of that needle touching that line or not touching the line. In this case, we are going to assume that the needle does not have a head. So if you take this needle and put it this way or rotate it 180 degrees and put it this way, it looks identical. And we are also going to assume that the floor is infinite in extent, that is, when we throw the needle, it will fall somewhere on the floor. It will not go to the edge of the room and put itself next to the wall. So we'll throw a needle on a floor large enough marked with parallel lines with line spacing equal to h, and the length of the needle is L. So when you throw this needle, you perform this random experiment. There are two random observations. There are two random variables that realize their respective values. One random variable is the distance between the center of the needle and the nearby line, the nearest line. You can formulate this problem differently, and you can say I'm going to observe the distance between the center of the needle and the line below it, or you can say I'm going to observe the distance of the lower point of the needle and the line below it. Whichever you choose, you are going to have this random variable lying between a certain values. For example, if you observe this piece of information, that the distance between center of needle and the nearest line, then this observation is going to lie between 0 and h by 2. H is the line spacing. So if you measure the distance between center of line and the nearest line, it's going to be h by 2 at most. The second piece of information is the orientation of the needle. This orientation is going to be between 0 and 180 degrees because we have assumed that the needle is symmetric. if we had a needle with one end clearly marked as the head, then the 360 degrees would have been the correct range of observation. But now needle placed like this or placed like this is same. So our range of observation for the orientation of the needle is a random observation between 0 and pi, 0 and 180 degrees. It is reasonable to assume that these two pieces of information, these two random variables, are going to be independent of each other, because once the needle is somewhere along the vertical direction, if the lines are horizontal, the center of needle is anywhere in the vertical direction, that location is not going to affect the orientation of the needle. The needle assumes its location vertically and its orientation independent of each other. So it's reasonable to assume that these two pieces of information, these two random variables, are independent of each other. Furthermore, it's also reasonable to assume that these two random variables are uniformly distributed. So first random variable, which is the vertical location of center of needle and the nearest line, is a uniform random variable between 0 and h by 2. And the second random variable is the orientation of the needle, which is a uniformly distributed random variable with values between 0 and pi. So the joint PDF will be a flat rectangular plateau with extent 0 to h by 2 vertically and 0 and pi horizontally. Horizontally, we can say it's a random variable x, which represents the orientation, and vertically it is random variable y, which represents the vertical distance between the center of the line and the nearest possible line marked on the floor. So what are the conditions that these random variables must satisfy so that the needle touches the line which is nearer to it? If you see the work done in your class handouts or in any other resource, you will see that it works out this way. Suppose there is a horizontal line which is closer to this needle, and needle has a distance of say x from its center to the nearer line. So x is the distance from the center of the needle to the line which is closer to it. And the needle is lying with such an orientation that it is making an angle theta. Angle theta is also with respect to these lines. So if it's making angle theta, then the distance from the center to the tip of the needle is L by 2, because the total length is L. And this vertical distance is L by 2 sine theta. So if x is the distance from the center of the line to the line on the floor which is closer to it, then the needle is touching the line if L by 2 sine theta is larger than this x. And this x is the realization of this vertical distance. So if this condition is satisfied, then the needle is touching the line which is closer to it. I have used this condition, and I have used a flat PDF on xy plane where x is from 0 to pi and y is from 0 to h by 2, and I have marked certain regions which represent that needle is touching a line, and these regions are marked for different values of lengths of needle. For example, the first case that you will see on the slide is when the length of the needle is half of the interspacing, the spacing between two nearby lines on the floor. This region is shown in red. So this region represents the combination of orientation and the distance from the nearby lines. For this combination, if that combination happens to belong to this red region, then the needle is touching this line. Similarly, the green region on the slide is the region where the length of the needle is assumed to be same as the spacing between lines. So L is h. With this condition, the green region as well as the red region. So the green region and the red region below it, they combinedly represent the event where the needle is touching the line, where length of the needle is same as the spacing between the lines. And the last region, which is blue, and this blue region in union with green and red region. So blue region and all the region below this represent the probability of the needle touching the line when length of the needle is 4 times the spacing between lines on the floor. For these particular cases, when the length of needle is half that of length of the spacing between parallel lines, the probability of needle touching the line comes out to be 1 over pi, which is 31.8%. And when the needle is as long as the spacing between the parallel lines, the probability of this needle touching a line is 2 over pi, which is 63.7%. And when the length of the needle is long, 4 times as long as the spacing between line, then the probability of this needle touching any line is approximately 92%. So as you can see, when the length of the needle is increasing, the probability of it touching any line is also increasing. So it will be interesting to plot this probability of needle touching a line as a function of length of the needle, where length is relative in terms of how many times the spacing. So if length is same as the spacing between line, we are going to assume a relative length of 1. And when it is 4 times the spacing between parallel lines, we are going to assume a relative length of 4. I have found these probabilities, and you can see the relationship on the next slide. This slide shows that when the needle length is very small, the probability of it touching any line is also very small, which is intuitively how it should be. As the length of the needle is increased from very small value to a relative length of 1, the probability of this touching any line also increases linearly, and it reaches a value of 2 over pi, or 63.7%. If the length of the needle is increased beyond this point, then the probability of needle touching the line does not go in a straight line fashion, it goes in a tapered, slowly increasing fashion. And if you take a very long needle, the probability of it touching any line will be very close to 1, but not exactly equal to 1, because there will be certainly some cases where even a very long needle may not touch any line. Remember, these lines are parallel and infinite in extent, so even if the needle is very long, it can certainly lie in between two lines with an orientation of almost 0 degrees, and it will not touch any line. So this probability of needle touching a line increases linearly, while the length of the needle is increased from 0 to a relative length of 1, and after that the rate of increase of this probability becomes less and less and less, and it tapers off and it approaches 1. If you are going to play a gambling game based on this Buffon needle, as people used to do in 17th and 18th century Europe, you should observe that if you take the length of the needle same as the spacing between the lines, the probability of it touching a line is more than 0.5. So if you are playing a gambling game like that, always wager that yes, the line will touch the needle, or needle will touch the line. The break-even point occurs when the length of the needle is approximately 79% of the spacing. So if the spacing is say 10 centimeter and the length of the needle is 7.9 centimeter, then probability of it touching a line or not touching a line is almost the same. So if needle is smaller than 79% of the spacing, then it is better to bet on the needle not touching the line. And if the length of the needle is more than that, then the needle will touch the line with a probability which is larger than 0.5. So far we have dealt with flat distributions, joint distributions which were flat in nature over a certain finite region of the xy plane. You can certainly deal with non-flat type of probability density functions, and you can generate them yourself, and you can have some of them from your textbooks or your class notes. But one thing you should keep in mind when you are generating such non-flat joint probability density function is that it should never have a negative value. For example, you define a region of x from 0 to 10 and y also from 0 to 10, and on that square region you want to define a non-flat PDF which is kind of a plane with some tilting angle, and you choose the equation to be 3 plus x plus y. So the joint density function, which is the density of x and y observed as a pair, which is function of two variables x and y, it is 3 plus x plus y. You cannot have that because in the region that you have chosen 0 to 10 and 0 to 10, this function 3 plus x plus y will give a total volume which is larger than 1. The joint PDF, which is a surface, a hill kind of thing, it should have a total volume of 1. So if you are trying to generate a non-flat PDF like this, you should put a k outside. So the PDF expression as a function of x and y will be k times 3 plus x plus y. So k times and then in the parenthesis 3 plus x plus y. And you can certainly find the value of k by taking this 3 plus x plus y, integrating over 0 to 10, 0 to 10, you will get a large number. That number should be 1 over k. You divide this expression 3 plus x plus y with 1 over total volume and you will get a valid joint PDF which is non-flat. And on this PDF you can define interesting events and find probabilities of those events. For this case, where the PDF was a scaled version of 3 plus x plus y and the region was 0 to 10, 0 to 10, this function had positive values only. But if you take the same region 0 to 10, 0 to 10 and have a PDF which is a scaled version of 10 minus x minus y, then you will have a problem. Because if you have this 10 minus x minus y as the fundamental function defining the shape of the PDF, it has potential to attain negative values over this 10 by 10 region. So you should be careful and you should use only those type of functions which do not give you negative values over the region over which you are trying to define them as PDF. And you should also have a scaling factor k, and you take the fundamental function, find the total volume in the region of interest, divide the expression with that volume to get a valid joint PDF of two random variables. You can generate non-flat PDFs using this, using simple algebraic functions like 100 minus x plus y, 3 plus x plus y, etc., etc. Or you can have two marginal densities, two valid properly scaled densities for x and y, and multiply them together to get a joint PDF. I'm going to use this second approach, and I'm going to use two exponential distributions for x and for y to get a joint density. And this I'm going to take for a case which was discussed a few lectures ago. When we were discussing exponentially distributed random variables individually, we said they model the survival times. They tell you at what time the component is going to fail with a certain relative likelihood. And when electronic components are new, they have higher relative probability of failing, and as they age, they have lower relative probability of failing. So exponentially distributed random variables are used to model the failure of electronic components. And if you remember, we took example of two television sets. The first television set was manufactured by a certain manufacturer, and we assume that this has a failure rate of 0.1. So its PDF was 0.1 e raised to power minus x over 10. So for this case, lambda was 0.1. So this is our random variable x. The other television set that we considered had a lambda of 0.05. So failure rate of 0.05. And the density of that PDF was 0.05 e raised to power minus y over 20. I'm assuming y because I'm going to consider pair of random variables x and y. So this joint density, which is multiplication of this marginal density of x and this marginal density of y, is a joint density of a random experiment of observing the failure times of two televisions. So it can model a real life situation where you have purchased two televisions, one from a more reliable manufacturer and other from a less reliable manufacturer, and you purchase two televisions simultaneously, bring them home, put them into service. And then you think about how they are going to serve me, which one is going to fail earlier, how long are they going to give me, the total service time, things like that. So if you take these two random variables and assume that they fail independent of each other, then the joint density is simply multiplication of the individual marginal densities. This joint density, which is a function of x and y, is shown in the next slide, which you can see on your screen. On this slide, you can see that this joint density is a kind of slope defined on a square region. Even though this joint density is defined for the whole first quadrant where x is between 0 and infinity and y is also between 0 and infinity, but we are going to show only a small region from 0 to 30 and 0 to 30. So 30 months by 30 months is the time that we are interested in, even though PDF is non-zero for all positive values of x and y. So this joint PDF has a peak at 0, 0, and then it slopes when you go away from this origin to values, positive values of x and positive values of y in the first quadrant. On this joint PDF, we can define interesting events, and I have manually colored the region of this joint PDF which represent some interesting events that we are going to consider. If you look at the slide, then this red region, which is towards the origin, represents the probability of both televisions failing during initial stages in such a way that total service time is 20 months. So your red region represents a random event where x and y take on values in such a way that the sum of the two values is less than 20. They can be 5,5, 13,7, 6,14. They can be any values as long as the sum is less than 20. So this red region represents the probability of both televisions failing in such a way that total combined service time is less than 20 months. So how do you find probability of such an event? It's not very difficult. All you have to do is take this joint PDF, which is function of x and y, and integrate it over this triangular base region where x is between 0 and 20, y is between 0 and 20, and then there is a bounding line which joins these 2 points, which is y is equal to 20 minus x. So this y is equal to 20 minus x line is the bounding region where this triangular shape region is representing the probability of both televisions failing in such a way that the total service time, the combined service time, is less than 20 months. So if you know how to integrate a function of two variables over arbitrarily shaped regions, you can certainly find the probability of this event. And in the earlier lectures, I said that when you are dealing with integration and other algebraic manipulations of the quantities involved, you should not lose sight of the ultimate goal of having an understanding of the underlying probabilistic event. So even though this integration will be slightly involved, but I want you to finish this, do it using either the manual pencil and paper route or using MATLAB, particularly the symbolic toolbox of MATLAB, and find this probability. I have found it and it comes out to be approximately 0.4. So there is a 40% probability that your television sets will fail in such a way that total service time, combined enjoyment time of the two televisions will be less than 20 months. Another interesting event marked on this joint PDF shown in blue colors is that suppose your televisions give you a combined total service time of more than 20 months, what is the probability that X will fail later than Y? So they are going to fail in such a way that total service time is more than 20 months. So that is represented by region away from the 0, point, away from the peak of this joint PDF. The region away from the red region, the blue and the gray region combined. Out of this combined region, I am interested in the blue region only where X fails later than Y. So they fail in such a way that total service time is more than 20 months. But what's the probability that X is going to fail later than Y? It turns out that this integration is even more involved. But don't lose heart. Sit down and carefully find this probability, and if you do, you will find that this probability comes out to be 0.16. So there is a 16% chance that the X will fail later on. What is X? X is the random variable representing the failure time of that television with a lambda of 0.1. So if lambda is 0.1, then this is more likely to fail compared to the other television which has a lambda of 0.05. Smaller the lambda, more reliable the television. So this blue region represents an event where both televisions give you a good service time, but the less reliable one fails later. That is strange. Actually, the more reliable one should fail later and less reliable one fail earlier. But in probabilistic theory, nothing is predictable. If the less reliable was always going to fail before the more reliable, then this will not be a probabilistic, unpredictable phenomena. So even though Y represents the failure time of the television which is more reliable, it's quite possible that the reliable one will fail earlier and the less reliable one fails later. And this has a probability of 0.16, only 16%. The last region of interest is shown in gray color in your slide, and this represents probability of Y failing later than X, where Y is representing the event where the more reliable TV is going to fail. So this gray region represents an event where the more reliable TV is going to fail later, and this probability comes out to be approximately 44%. You may be wondering that probability of more reliable TV failing later should be more than 0.5. But we have excluded some red region. 44% is the probability of the more reliable TV failing later than the less reliable one, provided that they give you a total service time of at least 20 months. If you remove this restriction of at least 20 months and just find the probability of Y failing later than X, it comes out to be 2 by 3. Now the region of integration is the triangular upper region. And if you find the probability of X failing later, that is less reliable one failing later than the more reliable one, it comes out to be 1 over 3. Today we discussed in more detail the problem of jointly distributed pair of random variables. We looked at examples where PDF was simply flat plateau or non-flat type PDF. In particular, we looked at the PDF, non-flat PDF obtained from two marginal triangular PDFs and compared it with a flat diamond-shaped PDF. We also introduced the non-flat joint PDF of two exponentially distributed random variables and defined interesting events on this joint PDF, which was exponential in X and exponential in Y direction. In coming lectures, we are going to expand this treatment of joint random variables which are continuous, and we are going to find more probabilities of other interesting events, and we are going to cover other interesting topics like correlation between two random variables which are jointly random. Till then, I wish you the best. Goodbye. Assalamu alaikum.